faculty members and my dear scholars. On behalf of the Department of Physics, I would like to welcome all of you to today's workshop on the Kelvin Probe Microscope Technology. I request the Honorable Chief Guest, Professor Subramaniam, to come and grace the dais. As a welcome gesture, I would like to call Ms. Supraja to give the fruit basket to the Chief Guest. Thank you, Supraja. I request Professor V.T. Somashekar to come and grace the dais. Now I would like to call Ms. Pooja to give a fruit basket to the Dean, sir. Thank you, Pooja. I request Professor T. Venkatappa Rao to come and grace the dais. Now let me call Ms. Rakshita to give a fruit basket to the HOD of Physics. Sir, please hands. Thank you, Rakshita. Now I request all of you to stand for the national song. Thank you, Rakshita, Payal and Anita. Now I request HOD of the Physics Department, Professor T. Venkatappa Rao, to address the gathering.
Good afternoon to all. We are here to, I welcome you all to the workshop on Kelvin Probe Technique, a non-contact and non-destructive surface analytical tool by Professor A. Subramaniam, retired Professor, Department of Physics, IIT Madras. Professor Subramaniam, an accomplished academician and researcher, a retired professor from Department of Physics, IIT Madras. His contributions are known to the world in the transparent conducting oxide films, field of photocatalysis, particularly lung-assisted devices and thin films. The Department of Physics, NIT Warangal, was started in 1959 and recently completed 63 years of its existence, and it produced around 150 PhDs, and it is offering MSc Tech Engineering Physics, integrated MSc Physics, as well as it is assisting BTech courses, BTech engineering courses. It is having 20 faculty strength. Now at present 17 faculty are working, and it is having about 50 scholars on rolls, and every year about 100 research publications are coming from our department. Now I request Professor A. Subramanian Garu to deliver his talk. Welcome, sir.
I think we have to be here till inaugural is over. I think Professor Somashekar, you have to come and address, then I will address. Come. Let us not go after the inauguration.
Respected Professor A. Subramanian Garu and the esteemed faculty members of the Department of Physics, Head of the Department Professor B. Venkatappa Rao Garu, and my dear student friends. When I learnt about this Kelvin Probe Probe microscope technique, my heart swells with pride, because we could bring down its price drastically thanks to the innovative and pioneering research made by Professor Subramaniam Garu. Prior to this, I understand that only one Irish company used to supply this, and they had a monopoly in the market, and they had their sway. Now I understand that because of the tremendous efforts made by Professor Subramaniam Garu, this price has come down by leaps and bounds. It has become so affordable that every institute now can think of leasing that particular equipment for the benefit of the student community in general and the faculty and the research scholars in particular. Of course, I would like to just say one thing in a lighter vein. I would like to quote Mark Twain. It's a very popular quote from him. He says that it's better to keep your mouth closed and appear as an idiot rather than opening it to remove all the doubt. I am really not a person to talk about the Kelvin Probe microscope technique, but I understand that it is of paramount interest in surface engineering. And as I see from the preface of that book which he authored, that surfaces are deceptively simple, and of course unless you probe them, you will not be able to know the true colors of any surface. And in that direction, I believe that he had made tremendous contribution. And what is very important and what is very heartwarming is that that contribution has come down to earth and has now become useful for the research community, because I'm emphasizing this because many a times out of all the research work that we do, very few things come to fruition. Okay, and this I believe is a great achievement on the part of the team and Professor A. Subramaniam Garu. I won't bore you more than this. Thank you very much for giving me this opportunity.
Thank you, sir, for your kind and inspiring words. Now I request Professor Subramaniam to share a few points about today's event. Welcome, sir.
Professor Somashekar, the Dean of R&C, and Professor Venkatappa Rao, the Head of the Department of Physics, my colleagues, dear friends, and those who are enthusiastic about this Kelvin probe, welcome to this great workshop. I have to say only two things. The only one person who can ask a remarriage on the day of the marriage is the photographer. You cannot deny that. And the person who dictates the inauguration function, you have to follow the protocol. No other go. You can't say anything. Is it not? I think we follow that. Thank you very much. And I think Professor Somashekar has told a lot of things about this Kelvin probe and about me. It's almost like this. When you get your shirt tailored by a person, by a tailor, you feel so proud and tell everybody this is tailored by him. Shirt is yours, you paid for it, but the credit goes to the tailor. Exactly the same thing happened with me. Students work hard on the lighter vein in a whisper, made me work harder, and the result of it is the Kelvin probe. I am also so thankful that we are the first people to write a book on Kelvin probe. We are lucky, I would like to say. So with this, I would like to say thank you very much for NIT Warangal and the team for inviting me here to share my thoughts. I'm a crazy guy, people know about it. And crazy persons do crazy things at the crazy times. So today afternoon, we would like to spend some crazy time with all of you, seeing 1890, Lord Kelvin set some basic principle, and 222, still a few people are struggling hard to understand and make it work. That is Lord Kelvin, and here we are. Now I take this opportunity to what should I say, give my heart, a little bit of my heart to Professor Somashekar and to Professor Apparao Garu by giving these books to them, authored by me and my student Suresh Kumar. Give me that. Okay, thank you very much.
I want to say one thing, like we all are lucky to have you as a chief guest for this workshop. So thank you so much, sir, for coming. No, just now you say na, sir. Like no, definitely all will say same thing what I said now. Thank you so much, sir. Now I request the faculty and the student of the physics department to felicitate the chief guest of today's workshop. Please come on the dais. Now I request all the faculty members to felicitate the Somashekar sir. No, directly we will start. Thank you, all of you. Our chief guest of the event, Professor Subramaniam. He is a retired professor from IIT Madras in 2019. Dr. Subramaniam, a senior professor, has teaching and research experience spanning over 36 years at the Indian Institute of Technology, Madras. His main areas of research are functional metal oxide thin films, surface engineering, and biomedical engineering. He has established a thin film laboratory equipped with electron beam evaporation, DC and RF magnetron sputtering, pulsed laser deposition, and sol gel techniques. Along with that, he has lot of research achievements, which includes he has 143 research papers in international peer-reviewed journals and has 8 patents. And along with that, he has guided 22 doctoral fellows for their thesis work. He has executed 48 sponsored research projects from the Government of India, including DST, DRDO, MIT, and also various multinational companies from GE, Essilor, PPG, Saint-Gobain, and HCL. He is one of the editors for Solar Energy Materials and Solar Cells of Elsewhere journal. He has been elected as a member of the European Joint Committee on Plasma and Ion Surface Engineering and the Asian Joint Committee for Applied Plasma Science and Engineering. Also a member of the International Advisory Committee of the Society of Vacuum Coaters from the USA and Plasma Surface Engineering, Germany. He has fabricated a commercialized Kelvin probe, a non-contact on and non-destructive surface analytical tool for metal and semiconductor surfaces. The first book on Kelvin probe is entitled with The Kelvin Probe for Surface Engineering Fundamentals and Design, published in 2010 by AnyBooks India and CRC Press USA. I am glad to say that Subramaniam sir is one of the authors of this book. He also developed a lung assist device using photocatalysis, early warning system on mechanical heart valves failure, and has also designed advanced cylindrical magnetron cathode for gun barrel coatings. His great achievements include some awards that are Young Scientist Fellowship Award by DST, Government of India in 1988, the Humboldt Fellowship from Alexander von Humboldt Foundation, Germany in 1989, Saint-Gobain Chair from École France in 2009, DAAD Professor at TU Germany in 2009 to 2010, SVC Mentorship Award from USA in 2021. Apart from that, he is the founder director of MS Thin Film Solution Consultants and Project Executors, incubated by IIT Madras in December 2013, and the foundation director of MS Softsyn Tech Private Limited, started in Bangalore in February 2016. There is nothing better than having someone with such a bright personality and achievements in between us. So, with great pleasure, I request Honorable Professor Subramaniam to enlighten us with his talk on Kelvin Probe Microscope Technology. Welcome, sir.
Thank you very much for the nice introduction, which is scary to me. Because when it is so nice, people have a lot of expectations, and I don't know whether I will stand for it or not. But let me try. So today afternoon, we would like to live and take a journey into Kelvin probe, a technique which is non-contact and non-destructive as a surface analytical tool. You must be wondering, there are so many techniques, and why only Kelvin? Kelvin is the only one which is non-contact, non-destructive. As I have given, this is the only technique which will leave the surface or the interface virgin even after the measurement. That is the beauty of this technique. So what we would like to do is, this entire presentation is divided into 4 parts. Part 1, I would like to just give you a brief introduction about surfaces and interfaces, how simple they are or how complex they are, what is that we are trying to learn from the surface and interface. Part 2, I would like to give the basic principles of Kelvin probe and a little bit of instrumentation, what goes into that. Most important, you may ask me where I am going to use it and what are the applications. That is being dealt in part 3. And part 4, okay, technique is there, applications are there, but how am I going to interpret the data? This is most important, because this is the part which will further or give the deep understanding of the technique, and the data what we get, we can really understand the physical phenomena, what is happening on the surface and interfaces. If time permits, I would like to give you a very brief introduction, which is an add-on or an accessory for the Kelvin probe called surface photovoltaic spectroscopy. As Kelvin probe is used for surface analysis in a non-destructive way, surface photovoltaic spectroscopy, which is a part of Kelvin probe, can be used for probing the interfaces without any destruction. Okay, so this is the most important part we will be dealing with in the next, I would like to say, couple of hours, if you allow me that. Okay, so let us start with part 1. Part 1, we would like to deal with surfaces and interfaces and introduction. Honestly speaking, this is all what you know about it. You know everything. Only point is, I have to uncover the part of what I am trying to ask you. Okay, I'm just going to uncover. So you already have most of this information with you. We are using copper vessels in our household, copper utensils. And whenever you want to drink water from that, it doesn't look like copper, but it gets blackened, because copper gets oxidized. Similarly, the silver gets sulfurized. So these two metals, when they are just exposed to the atmosphere, over a little bit of time, maybe a few hours, they get tarnished. We call it as tarnished. Chemistry people call it as oxidized. Same is the case with iron, Fe, ferrous or ferric. I am neither a chemist nor a physicist, nor a material scientist, nor a biomedical engineering. I am none of these, but still I speak about all those things a little bit here and there. Okay, so bear with me. If there is any chemist in the audience or anywhere who is participating, will come to know what exactly oxidation, reduction, how the oxygen interacts with iron to form iron oxide, which we call it as corrosion. You know, oxidation or corrosion is a physical process which has a exchange of electron from the metal to the oxygen. There is an exchange of electron. In order to have the exchange of electron, there must be some energy. Where is this energy coming from? This is the main topic on the surface engineering. And sometimes you want to clean the surface, sometimes you want to protect the surface, sometimes you want to modify the surface. I don't have to tell you, the surfaces are almost $1 billion industry. For example, take silicon. Silicon surface, whatever you do, just leave it onto the atmosphere, it gets silicon oxide of about something like 1 nanometer thick maximum. And this 1 nanometer thick silicon oxide is the one which is controlling the multi-billion-dollar industry of silicon. You may call it as microelectronics, you may also call it as nanoelectronics in the future. So when you come back to the surfaces, you know copper, silver, iron, they get oxidized. Then you may ask me a question, what happens to gold, platinum, rhodium, all these precious metals? Are they also going to oxidize? If they oxidize, how much time do they take? Then the natural question comes, why do these metals oxidize? Why don't they keep quiet? They should keep quiet. You keep copper there, you didn't ask copper to get oxidized, but it gets oxidized. Okay, we are going to ask the question, what happens at the surface level with reference to the reactivity with the either the ambient gases or with the intentional gases, or even with some of these liquids which are flowing through. Now coming to, you may say, oh, copper is okay, gold is okay, their materials are used only in the laboratory, but not for many precious applications. I don't care. But remember, there are metal implants in the body, lot of metal implants. Okay. Now we would like to correlate when iron is exposed to oxygen or iron is exposed to humidity, it gets rusted. If iron is exposed to salt water, it gets chlorinated. When a metal is exposed to blood and the body fluids, it also gets the oxygen, because body fluids contain proteins. So the proteins are going to interact with the metal implants. They may do lot of good things or bad things to these metal surfaces which are available in the implants which are living in the body. This body is yours and mine, remember that. Now you can't say whatever be the surface of the metals, I don't care. You have to care, is it not? So therefore, just have a look at, so many metal implants are there in the body. I don't say everything is available in every body, but whenever you play football without real coaching, you are bound to have a fracture. If you are having a fracture, I mean, I say football, but the fracture can also happen in any fashion you feel like. Then there is a metal implant. If there is a metal implant, psychologically you feel there is a metal implant in me, and how is it going to behave? Do I get a guarantee or warranty for the metal implant when I got operated? Probably no medical doctor will be able to give it, no medical company will be able to give it. Why? Because the body fluids for every body are unique in their protein structures. Okay? So therefore, it may not be possible for me to postulate, okay, if you use this, you are going to get this implant running for so many years. No. There are many people, many implants are being rejected every year, every day. For example, we have collected quite a good number of rejected implants from the patients, and it is very torturous. Okay? So therefore, surfaces are most important. Now you may ask me, okay, you told about oxidation of copper, oxidation of silver, sulfurization of silver and oxidation of iron. The metals what we use in the human body, the implants, they are made of titanium. Titanium doesn't really matter. It is a material which does not oxidize, which, I mean, it's very robust. It's a biomaterial. But it can also oxidize. It can also corrode. Why it can corrode? In fact, there is a book, Tribocorrosion in Biomaterials and Medical Implants. Tribology is a subject. Now there is a group working on tribo energy in NIT Warangal. So tribo is something which is expanding into several fields, including corrosion. Let's have a look at it. Mechanically assisted corrosion is is everywhere, is not only limited to orthopedics. Okay. This mechanical assisted corrosion, also known as tribocorrosion. Tribocorrosion is coming because of various stresses and strains which the metal surface is going to undergo, and it can also give you a corrosion. When corrosion is divided into several categories depending upon how the oxide goes into the lattice. It is fretting corrosion, fretting service corrosion, lot many things are there. So we should understand how the surfaces are behaving under different conditions. There is total hip replacement, mechanically assisted crevice corrosion, totally hip replacement, the clinical and retrieval view. So the point is, if it is a corrosion only with the utensils or whatever I use outside, we can live with it. Of course, we cannot live with it if there is a crude pipeline is getting corroded and gets damaged. All the crude will be lost. So that is the bigger problem. More important problem is if the metal implants are going to be corroded, they are going to be rejected by the body, and that rejection will give you a lot of pain that you cannot. So what is that we are trying to learn about these surfaces are, metal surfaces do interact with ambient oxygen, sulfur or any reactive gases and results in oxidation, otherwise known as corrosion. Tissues and several proteins in biological systems also interact with metal surfaces. They also can give rise to what is called biocorrosion. This is what we are going to deal with. And marine environment, for example, you take a ship. The ship body is going to face two types of harsh environments. One is the saline water, it gets corroded. The other is this algae and all this marine aquaculture is going to be deposited on the surface of the metal, and that brings up what is known as biocorrosion. So corrosion is everywhere. If you want to really protect it from corrosion, you have to understand what's happening. If you want to understand it, you have to make certain measurements. These measurements so far are being done by techniques like X-ray photon spectroscopy, XPS, or scanning electron microscopy. Remember the fact, whatever are the surface analytical tools we are using today, they require a probe, they require vacuum, and the moment you put a probe on the surface is going to be modified. You cannot reproduce the surface, and surfaces are very complex. We are going to see that in a moment. So if you take semiconductor surfaces, they also deal with ambient gases. For example, in catalysis, you are all dealing with titanium oxide, a wonderful catalyst. These catalysts also have what is called the charge exchange process during the oxidation reduction mechanisms. And there are several interfaces are being formed, PN junctions, Schottky's, heterojunctions. And semiconductor liquid interfaces is an electrochromic and electrochemistry problem. Today, what is going to happen is, if you want to make a tailor-made material, you have to modify the work function of the surface of a material. There is a big requirement for that. So now, first when we started this course, we asked one question. There are certain surfaces which are being more active for oxidation, some are not. These are more active on oxidation, we call them as active surfaces. Come on, sir, you are always categorizing something and making it complex. No. What is known as, there is surface energy. The surface energy plays a major role. If the surface energy is high enough, it can react with ambient gases very quickly. For example, if you take silicon, keep it in the ambient, wait for a few milliseconds, silicon oxide is formed. Take gold, you wait for about an year till your spouse says, I need it to be polished. Then you have to go to the goldsmith, ask him to polish it. While polishing, what he does is, he is not going to change the surface, he is going to remove the surface. So practically, when you are changing the surface, when you are removing a part of the material, the goldsmith is getting the benefit of charging you for polishing, and also taking away the gold whatever he got. Maybe a few micrograms. If you make it for 1,000 people, he get grams. So we call the materials or the surfaces active when they interact. These active surfaces do have what is called high surface energy. This high surface energy, the basic principle is, why do they react? Are they crazy to react with oxygen? Are they not crazy to react with nitrogen? It all depends upon the chemistry. And how long is it going to interact? For example, I put a silicon, I wait for a minute and say, silicon, silicon, have you interacted? Have you finished your interaction? Silicon will say, come on here, I finished it long ago, it takes only milliseconds. How could you do that? Because my surface energy is so high, and I have a basic principle of minimization of energy from thermodynamics given by Gibbs. That's what we say. Every system, both surface and bulk, of any material should attain thermodynamic equilibrium. If it attains thermodynamic equilibrium, the changes that what we are looking at are going to be very, very slow. Don't think that they are going to die down. They will be so slow, we may not be able to follow them. For example, for gold, you have to wait almost for about 6 to 7 months to get it oxidized. Gold also does oxidized. So the question we say in thermodynamics is the minimization of energy or thermodynamic equilibrium. We have to bring the surface and the bulk, then it is going to be reasonably stable. Some basic questions we ask is how active the surfaces are. Can the surfaces be modified to achieve thermodynamic equilibrium? Can we engineer the surfaces, and how do we characterize the surface? These are the 4 basic questions we would like to ask about the understanding of how a surface should look like and should behave, and it should be under our control. Among the 4 questions, I would like to concentrate on the last question, how to characterize the surface. I would like to add a little more boundary condition for that. How to characterize the surface without touching the surface. My condition is, even after I conduct the experiment, the surface should be virgin. It should not lose its properties. How do I do that? That's the main question. Of course, you know the answer. The answer is Kelvin probe. Now, any of these oxidation reactions at the surface interface involve charge transfer process. You have lots of reactions where you deal with in a daily life which are having charge transfer processes. Number 1 is your photocatalysis or catalysis, and number 2 is your protein interacting with your implant. So there are so many places, whatever you do, and for example corrosion, oxygen is interacting with iron to form iron oxide, copper interacting with oxygen to get copper oxide. So wherever there is a charge transfer process, you know that we have the Helmholtz double layer is formed, charge is transferred. Once the charge is transferred, thermodynamic equilibrium is established. Once it is established, the system comes to a good rest, and the properties whatever you are measuring are the properties of the materials or the systems or the surfaces or interfaces where it is having a thermodynamic equilibrium. That is the whole process. So the main concern for us to understand the metal surface, because metal surfaces are most interesting importance and they have lots of applications, and you have interfaces, metal to metal, metal to semiconductor, metal to liquid, metal to anything, and modification of metal and semiconductor surfaces. For example, if you ask the question, if I can change the surface in such a way, I can restrict the interaction. Fantastic, that's what we are looking for. Okay, this is what we call as protective coatings on surface. What all we are doing is we are preventing the surface to interact with the ambient in such a way that the surface itself is getting a thermodynamic equilibrium by a coating. Okay, this is the main concern about the surfaces. So in fact, I have already told you about this. There are several techniques to study the surfaces: X-ray photon And most of the techniques after the study modifies the surface because of the probes. We will be happy if the surface remains virgin. Now, one more question comes, sir, if you leave copper in the oxygen ambient, like in atmosphere, it gets oxidized. Can you follow this oxidation process? Because it's a little slow, not as slow as gold, but not as fast as iron. Can you follow it? There is no technique which can follow that, remember. Only under the extreme conditions of controlled experiments you can be able to do that, but under ordinary conditions you may not be able to do that. Whereas Kelvin probe will be able to do you can follow the dynamic oxidation conditions. I am going to give you the example when we go for the applications. So far so good. We have set the stage for Kelvin probe. I have advertised enough. Now let me go into the product, because if I start advertising, you may say, okay, come on, let's see what exactly is in the kitty, rather than showing you something and not showing you something. What we measure in Kelvin probe is the surface work function. Probably I should ask you and me to go back to our 10th standard physics and chemistry, where we defined what is the surface work function. I'll tell you, don't be in a hurry to ask me all the secrets, because story slowly unfolds. Okay, so Kelvin probe, we are going to measure the surface work function, which will give me the electrical signature of the surface. That's beautiful. Now, if I want a chemical signature of the surface, do Raman spectroscopy. So, if I have Raman and Kelvin together, how is it going to be? It is going to be a wonderful idea to have the chemical and electrical signature together. Wonderful. Both the techniques are not going to change, not going to modify the surface. Good. So, the application areas of Kelvin probe are many. Start with interface probing, adhesion and corrosion, photocatalytic activity, surface defects. In one single word, wherever there is a charge transfer process, Kelvin probe can be used. Whether it is biology, whether it is chemistry, whether it is physics, whether it is chemical engineering, whether it is mechanical engineering, wherever it is. Okay? Good. Fine. So, part 1 of the story, I took almost about 20 minutes to tell you. Part 2 of the story, I will take a little less time, because this is the basic principles, and the saying goes, whatever basic principles you say, I don't understand. Okay? So, let us try. So, the basic principles of Kelvin probe, I would like to quote Lord Kelvin, one accurate measurement is worth 1,000 expert opinions. So, if you can really make one good measurement and understand it and analyze it, the interpretation of the data is so beautiful, you really admire it. And this is what we get in academia. Academia, the beauty comes only when you understand the basic principle, analyze, get data, and then give a complete understanding of what it goes. Okay, Kelvin probe measures work function. And what is work function? Work function is, before I define the work function, in our 12th standard now, and my senior colleagues during our bachelor's course, we studied that any semiconductor, which is a single crystal semiconductor, will contain band picture or band theory. What all it means is, the electrons which are flowing, which are conducting, which are responsible for electrical conduction in a semiconductor follow certain rules, and one of the rule is that the free electrons are not having a single energy, they will have a band of energies which are allowed. And how many electrons are there? Because this is a semiconductor, it can have positive electrons, we call them as holes, and electrons. So, in order to count how many of them are there, maybe we can say in a crowd of say 100 people, how many women are there, how many men are there? How do you do that? By statistical methods. So, what do you ask? You ask a question, if what is the probability of finding the electron with a given energy which is responsible for conduction, if I know the probability in that energy scale, that I would like to call it as a Fermi level. What is a Fermi level? Fermi level gives you an idea of how many electrons can be conducting in a given semiconductor. If not only electrons, even the positive holes. What do you mean by Fermi level? Fermi level gives an energy level which is an average, which tells you whether electrons are dominating or holes are dominating. You know that there is a conduction band and there is a valency band. This conduction band and valency band together we also studied with reference to the bond theory. If an electron is bound to the nucleus, how it is bound, we can also say how the bands are. Band is only a concept. If you cut a crystal, there is no band at all. It's only the energy of the electron. We map it, that we call it as a band energy. Now the probability of finding the number of electrons and the number of holes put together, that probability, if it is equal, half and half, we call that half level between the conduction band and valency band as the Fermi level. So Fermi level is a energy of the electron exactly half between the conduction band and the valency band. For example, if the electrons are more, the Fermi level goes towards the conduction band, and if the holes are more, the Fermi level goes towards the valency band. This is what exactly has been measured here. Now the work function we define as the amount of energy required to remove an electron from the Fermi level to the vacuum level. Ha! Subramaniam, you are now is a real good physicist. A good physicist is the one who gives a definition, and he defines the definition as a definition is because it is a definition, and it is a definition, and you have to follow the definition because it's a definition. As simple as that. So Fermi level is a Fermi level because it's a Fermi level, and it is a Fermi level, and you have to follow it in order to understand the Fermi level and the work function. You got it? I hope you got it, and I am very sure all of you are intelligent people, and I don't think any one of you have any doubt on this. Any doubts? I am sure you don't say yes. Okay? Anyhow, come back and go back to our school and college level and define the amount of energy required to pull an electron, because the electron is bound, it is having a negative energy, to pull an electron from the Fermi level into the vacuum level. What is vacuum level? Vacuum level is the level where the electron can go very freely. There is no periodic potential it experiences. It's almost like we all people after 6 o'clock. After 6 o'clock we have no class, no teacher, no guide, just pull off. That is the Fermi, that is the vacuum level. What is the bound level? Morning 9 o'clock, the first class in physics. You have to be there, whether you like it, whether you listen to it, whether you, because 9 o'clock you can't sleep, that is another problem. Okay? So that is what is called the electron in the conduction band or in the valency band. So the amount of energy required to raise an electron from the Fermi level to the vacuum level is called the work function. If the Fermi level is at the surface levels, we call it as a surface work function. If the Fermi level is in the bulk of the material, we call it as a bulk. Because you know the surface is different and the bulk is different because of thermodynamics. Because on the bulk there are lot many electrons, and the bulk has to have a thermodynamic equilibrium much faster than the surface. Because the surface, on the top of it there is nothing, only the ambient. So therefore it interacts with the ambient. Kelvin probe is a non-contact, non-destructive tool to measure the surface work function. Okay. Now you may ask me, why you are mentioning surface, surface, surface? Because whatever is the good thing done, as in silicon, or the bad thing done, as in your implants, this is the surface which is making all the difference, not the bulk. So if you can coat a surface with something else, the interaction fields, the coated material itself is the surface, not the bulk of it. So surfaces are most important. Now coming to the basic principle, 1897 None of us were there at that time. Probably we were there in a different form. I don't know. This Lord Kelvin, his original name is not Lord Kelvin. His name is, anybody? Hey, come on, you know it and you want to test me. Okay, let me answer. You are asking the question. Lord Kelvin's name is Thomson. Thomson is a very renowned scientist. He is renowned when he was taken the project of underwater cable from London to New York. He made it very nice. At that time it was a communication cable, and Queen was so happy with him. He said, okay, I will give you the lordship. When they give the lordship, they can also choose their name. And Thomson is very fond of a river called Kelvin. This is a river in England. So he said, Her Holiness, Her Majesty Queen, you call me Lord Kelvin. That's how he became Lord Kelvin. And Kelvin, we use it for temperature, and for all the scientific terms, we use Kelvin rather than Thomson. Okay, that's the beauty of Lord Kelvin. Lord Kelvin in 1897, he was conducting lots of experiments. One of the experiments he has conducted, when two metals of dissimilar work functions are electrically connected, then electrons from a higher work function metal flows to a metal having a lower work function. This looks absolutely Greek and Latin. Am I right? Those who have not understood, raise your hands. All hands will be raising. What is this work function? Why it flows? What is all that? Don't worry. I'll read it once again. I will go to an example. So every one of you, every one of us will understand that. When two metals of different and dissimilar work function are electrically connected, electrons from a lower work function metal flows into the metal with a higher work function till thermodynamic equilibrium is established. Those who have seen 3 Idiots movie, this is just looks like a definition for that. He defines what is a book. It looks like that, but not so bad. Okay, let me not show this. Let me go back to this. For example, you take a U-tube. Now you can't ask me, I can't take a U-tube. You must take a U-tube and pour water, or else take 2 single tubes, 2 different water levels, connect them at the bottom, then look what happens. Subramaniam, we are all graduates and postgraduates. What is the question you are asking? Are you a stupid? Probably yes, I am. But entire basic principle of Kelvin is here. You take 2 different tubes, 2 different metals of different work functions. The water level in one tube is lower, the water level in the other tube is at a higher level. The work function of copper is lower, the work function of zinc is higher. Now you are connecting the 2 tubes together, so water can flow from one tube to the other. You are connecting copper and zinc, 2 dissimilar metals having 2 different work functions electrically. Like the water flows from a higher column to a lower column till the 2 columns are equalized. Exactly the same thing happens. The electrons from a lower work function goes to the metal of a higher work function till they get thermodynamic equilibrium. Here comes a small problem. For water you set higher level, and for work functions you set a lower work function. I said it because the lower work function, because the electron is bound, the value is negative. So a lower value will have a higher potential. That is the reason why I am using this word. So now you can understand it very easily what exactly is happening. So system 1 is my copper, system 2 is my zinc. Before they are connected, they are okay. The moment they are connected, electrons from copper has gone to zinc, copper became positively charged and zinc become negatively charged. Okay, this is what exactly Lord Kelvin said. And if you can measure the charge which is flowing from copper to zinc, you can find out the work function of copper with reference to zinc. Okay? So therefore, this is what exactly I meant. When you say when the two water levels are equal, the same thing I would like to call it as the thermodynamic equilibrium is established, which means the two Fermi levels are equalized. That's what exactly is happening. When two Fermi levels of the two systems connected electrically are the same, we said thermodynamic equilibrium has been established. Now, we say, let us try to understand what exactly is happening. You take the top plate as copper, positively charged, bottom plate, what I mean is here, this is the number 1 is the copper plate, number 2 is the zinc. Now, there is positive charge, there is negative charge. So therefore, there is a electric field coming from positive to negative. Okay. So you can calculate the potential between the two plates as QD by epsilon naught A or FD, and this delta V or the potential is called contact potential difference, because this voltage is coming because of the charge carrier movement, and the voltage is developed because of the contact between the copper and zinc. So this is called contact potential difference. This is what exactly we measure in Kelvin probe, and contact potential difference can be converted to work function. Okay. So what is that we are measuring? Contact potential difference. Why contact potential difference? Because when you connect two different metals, there will be a potential developed because of Kelvin's principle, because there is a charge transfer process. That is what we are trying to measure. Now, what we would like to call this as a Kelvin capacitor, I am calling it, to distinguish it from ordinary capacitor, because ordinary capacitor, the two plates are made of the same material, so there is no charge transfer process between the two capacitor plates. Now, since I am using two different plates of gold and my sample, there will be a charge transfer process. So surface work function measurement is always done with a reference. This will make it very simple. I would like to call the system 1 as a tip, because we would like to scan. The tip is going to give you lot of small areas. I can find out local variations. System 2 is your sample. So system 1, I call it as a tip. So phi sample, what you are trying to measure, minus phi tip is equal to Q CPD. Q is the charge, CPD is the voltage, so therefore energy balance is there. Now phi tip is known, it is about 4.51 electron volts. You can calibrate it and you can get it. So with reference to 4.51, what will be the sample work function we can measure? So what is that? I mean, you don't have to take gold, you can take platinum, you can take titanium, you can take tungsten. You can take any metal which will not change its surface properties as a function of time t. Now you may ask me, can I take graphene? Yes, you can take graphene, no problem. Okay. So now the things are very clear. By Kelvin's basic principle, you can formulate a capacitor. In the capacitor, plate 1 or the tip is a material of known work function. Plate 2 or system 2 is my sample. With these two, I can measure the contact potential difference. I can calculate the work function. If I know the work function, what do I know? I know the Fermi level. If I know the Fermi level, what do I know? I know the charge carrier concentration. What is this charge carrier concentration? This is the charge carrier concentration. How much charge has flown from sample 1 to sample 2 under the given conditions. So therefore, I can quantitatively say how much charge is transferred. For example, if it is your photocatalytic process, by shining light, there is a charge transfer process. So what is happening? Fermi level changes, contact potential difference changes. If you can measure that, you can find out how much charge has moved. This is exactly our problem in photocatalysis. If you can enhance it, your oxidation will go up. So our interpretation of the charge transfer process through Kelvin probe is one of the most powerful techniques. Now you may ask me, if it is so powerful, why people are not using it? Why it was not coming into the picture so far? It is because people thought the technique is not reliable to reproduce the results. people thought the technique is not reliable to reproduce the results. No, that's a wrong concept, wrong conception, because the technique is reliable. Why the technique is non-reliable? After all, I can't say after all, it is electronics. Electronics has to produce reliable results. Then why am I not getting repeatable and reproducible results? It's not because of the technique, it is because of the surface. If you can keep the surface reproducible, you can get reproducible results. No big deal. For example, you measure on gold to gold. You can repeat it. You can make the repeatability of the results as many times as you want. Okay? So this is the basic principle. I think I told you about the story of Fermi levels and equilibrium charges, so I'll skip this. Okay. Now comes, tell me when we would like to have the break. I mean, you please caution me, we will. Fine. We will complete the story part 2 and then we will have a break. So now you know very well doping or the electron concentration and the hole concentration, if you modify, what is going to change? Fermi level is going to change. If the Fermi level changes, work function changes. Okay? So now I will give you N-type silicon and P-type silicon. See the Fermi level, see the work function 4.15 plus minus 0.56 minus phi f, and this is plus phi f. If phi f is of the order of something like say 300 millivolts, it will be of the order of about 300, 400 millivolts. Now you can clearly mention 300, 400 milli electron volts is the movement of the Fermi level with the doping concentration. So easy. It's not at all difficult. Now because you understood Fermi level, now you can calculate quantitatively how much electrons are coming up. In our part 4 of the story, I will tell you how to calculate that. Okay. So what is that you are trying to get? You are trying to get the quantitative measurement of how much charge has been transferred in the process of you are making a catalyst, of you are making a tribocorrosion, you are making how the surface is modified. I can also say the same thing. If you want to modify a surface by any means, you can also measure the work function and say whether the surface is modified or not. On both the ways. If you want to say if there is a biocorrosion on my medical implant, what you have to do? Measure the Kelvin probe. If it is different, yes, there is a biocorrosion. So this method is affirmative in giving you a charge transfer process, and you can measure it, you can quantify that. This is what I would like to know. Now you may say, how do you do that? Really you can count all the number of charges? You need to have a model. Without a model you may not be able to do anything. In the sense, you have two questions now. Question number 1, why the surface is so active? How do I really understand that? You have got the observation, but you have not understood it. What has not been understood? Why iron gets corroded? Why copper gets oxidized? Why silver gets sulfurized? These are the observations you have, but you have not really understood what actually goes. Why the surface is going to attract my oxygen? How much oxygen? So therefore, if we can make a model, that model can explain both theoretically the experimental observations. One of the models we have is the surface dipole. So what is the surface dipole is, as I already mentioned, what all we know about it is, the bulk and the surface are completely different. Why? Bulk has a thermodynamic equilibrium much faster, a surface has having a lot of surface energy. I am using the word surface energy quite a number of times. You should ask me, or you have this question, if the surface is having energy, can you measure it? Because you tell me, you said one accurate measurement will answer lots of questions. I don't have to consult 1,000 people. What is surface energy? Can you measure it? I will answer this question in part 3. If there is a surface energy, what is the surface energy doing? How does it really come up? The surface energy comes up because of the formation of a dipole. What do you mean by a dipole? these surfaces, if they become negative, they attract positive charges. If the surfaces are positive, they attract negative charges. So the surfaces can be classified as anodic or cathodic. Okay. If we know what is anodic and cathodic, honestly speaking, for a given metal we do not know. We can measure the contact potential difference. If the contact potential difference is negative or positive, we can say the surfaces are cathodic or anodic. So the surface, the model what we are going to propose is the simplified dipole model. In fact, those who would like to know about more of it, Lang and Kohn has given a complete story about it in Physical Review B in 1970 itself. So the dipole layer, and you can't say that I have a clean surface. Surfaces are always dirty. Surfaces are always having lots of defects. These defects can be impurities, for example CXHY, polar molecules, and there will be a monolayer like in silicon dioxide. So what is going to happen is an electron goes from the bulk onto the surface to get it charged. Once that is charged, you are going to have either cathodic or anodic surfaces. Let me just give a very brief introduction about that cathodic, anodic. Okay, now I'm going to give it in my part 3. So the surface dipole formation is going to give you the entire story about how the surfaces are going to be active or non-active. Okay, I may take another 2 more slides to give you to answer the question. If Kelvin probe is so beautiful, so versatile, so powerful, why people have not used it for over the past 130 years? What is the reason? The reason is instrumentation has not developed. What is that you have to measure in Kelvin probe? You have to measure the number of charges which are flowing from one plate to the other. How do you measure the charge? What is the instrument we use to measure the charge? Electrometers. Why electrometers are not so sensitive? Because if you do the calculation, probably I will show you the calculation, you have to have something like 10 to the power of 8 electrons are moving. 10 to the power of 8 electrons can you measure? Difficult. Very difficult. Because it is a static charge. Static charges are not so easy to measure. Here one more question. Why don't we talk about insulators? We will certainly answer this question after the break. So now coming back to the instrumentation, we are measuring the surface work function. Yeah, here are a few numbers. Before you go further, ask a question. Why the Kelvin probe could not be done 50 years back? Because the capacitance of this entire thing is going to be about 0.093 picofarads. You have to measure that, almost coming into femtofarads. And if you calculate with these parameters, the number of electrons you are going to get, the flow, is of the order of 6 into 10 to the power of 5 electrons. Impossible to measure through any electrometer. Because of these two reasons, lowest capacitance and lowest electron number, instrumentation did not develop. Honestly speaking, the electrometer amplifiers started coming only in 1980s. Then the instrumentation has started. So yeah, 1932, Gisman from MIT has suggested, okay, there is a capacitance, Kelvin capacitance. If you can take the time variation of the capacitance, C is dC by dt, then because capacitance is equal to charge by Q by V, charge divided by the potential. If you take the time differential of capacitance dC by dt, there will be dQ by dt term, which is nothing but the current. So if you can mechanically vibrate one of the capacitor plates of this Kelvin probe, you can generate a current. That current can be measured, because current measurement is a little more easier than measuring the charges. That's how the instrumentation started developed from 1932. This is a simple picture to give you how the variation of time variation of capacitance with time is going to give you the current. And the current is of the order of femtoamperes. And remember one thing here, the moment you start vibrating the capacitor plates, what is that you are trying to do? You are trying to do in terms of the frequency domain. There is a frequency for the capacitor plate, but how you are measuring the current in the time domain, this is an average. So how do you go from frequency domain into the time domain? Through Fourier transforms. So if you can take the Fourier transform of the mechanical vibrations, then it will give you time averaged currents. That's the reason why we have the Fourier transforms coming into the picture. In the Fourier transforms, you have to worry about the coefficients. How far the coefficients, how many coefficients you have to take in order that the series are going to converge. So all those things we could do, and finally what we are trying to do is we vibrate the capacitor at 130 cycles so that no interference, no harmonics come into the picture, and we can measure 400 picoamperes. That's not difficult, at least nowadays. So therefore, from 1937 till almost 2000, it took lot of time for us to measure 400 picoamperes of current. That's the reason why instrumentation got a little delayed. There are quite a number of studies on improving the Kelvin probe work function measurements reliability. Reliability is always there, only the surface has to be reproduced. So there are lots of studies, let's not go into that. This is more or less my last slide in the part 2 of the story. You said work function. Tell me how many other methods are available to measure the work function. Totally there are 7 methods. Among the 7 methods, 6th one is the Kelvin probe microscopy. 7th one is scanning probe Kelvin force microscopy. Both of them look alike, but they are different. Because in Kelvin probe microscopy, we calculate through the change in capacitance as a function of time t. And in scanning probe Kelvin force microscopy, we measure the electrostatic force between the plate 1 and the sample. So we do with the force. Those who are interested, ask me, I will give you more of the details. Okay? So I answered the question. The basic principle is simple, but the instrumentation took a little bit of time because we have to measure lowest currents. Of course, charges we can't measure. At this stage, I would like to stop it after part 2 of the talk. Part 3, we will go into the applications where Kelvin probe can be employed. This is of more interest to us. We will continue it after the break. Okay? Thank you.
Now there is 10 minutes break for tea and snacks, and kindly come back for the next interesting part of the Thank you.
basic definition or basic Kelvin's principle is, if two metals or semiconductors with a different work functions are connected electrically, there will be a flow of electrons. So we are forming a capacitor between the two systems, and one of the plates is our sample. In the instrumentation, what we do is, the sample part of it we will earth it, so that if this is negatively charged, we measure the potential only with reference to the positive plate. That also we can measure it. So this is what we have done over the past 1 hour. Now let me go into the part 3, applications where Kelvin probe can be employed. This is more important because this is where you are really going to make use of this Kelvin probe as a technique. In fact, I can make at least about 30 examples, but due to lack of time, I would like to restrict myself to about 6 examples, in which I would like to emphasize more on the emerging topic of protein metal interactions. So what is that I'm going to show you in terms of examples is HOPG scan. HOPG stand for highly oriented pyrolytic graphite. Why HOPG is important? Because the work function of HOPG is constant. It won't change with the ambience, and this is used as a reference material for any of the surface work function measurements. I will show you how the Kelvin probe can measure the HOPG. Then I will show you metal on a semiconductor. For example, take silicon and deposit aluminum on that. The work function of silicon is different and the work function of aluminum is different. Can you distinguish between these two by making a Kelvin probe measurement? Like that, I will go for electrochromics, surface modification, whatnot. The underlying principle in all these examples is there is a charge transfer process taking place between this sample we are using and the reference electrode, reference plate. A reference plate is generally made of gold. People also can make it with tungsten, and they can also make it with any of the refractory metals where the metal is not going to change its surface with the ambience. Okay. This is the HOPG scan. What all it shows is the work function of HOPG is a constant one over a large area. The area we have scanned is about 3 mm by 3 mm. It took us almost for about 35 to 40 minutes to scan it, and the z-axis, actually this is a 3D plot, the z-axis is going to give you the contact potential difference. From the contact potential difference you can calculate the work function. The second example is we took silicon and we deposited with a mask the name IIT and we scanned it. You can see wherever there is a change in work function, the mapping of the Fermi level has been done by the Kelvin probe. So it can do IIT. In fact, we took silicon and put dots of aluminum. So wherever the dots are there, we can map the Fermi level and you can see the difference. So to say, in a scanned picture, this is the type of picture you are going to get. And z-axis is always CPD, and note down that the CPD is positive or negative depending upon whether the surface is anodic or cathodic or anodic, and the scan area can be different. I have scanned 5 millimeter by 5 millimeter. You can scan 1 centimeter by 1 centimeter, whatever it is. So gold and aluminum coated on silicon, it shows the difference. This example is actually, I have taken it from electrochromics. Electrochromics is the energy efficient methodology. What it means is, you take amorphous tungsten oxide, amorphous, and try to push either hydrogen ion or lithium ion. Hydrogen is H plus and lithium is Li plus. If these positive ions move into the tungsten lattice, the tungsten is going to change its color. And how do you push this hydrogen or lithium? Through an electric field. That is the reason why it is called electrochromics. That is, by applying an electric field, you are pushing a positive ion into the tungsten oxide lattice. If you are pushing positive, what is going to happen to the Fermi level? Fermi level has to come down towards the valency band. So there is a change. That change has been brought over here because we need an electrode which is transparent and conducting. We have taken tin doped indium oxide ITO, and then we coated the tungsten oxide on ITO, and a part of the tungsten oxide we took a drop of hydrochloric acid. So in the and then we put a circuit, that is some electrode will come and it is going to put at the bottom with ITO through a battery. We push this hydrogen ion into the tungsten lattice through some electric field. Then this tungsten oxide becomes bluish in color. When you put the reverse voltage, the whatever is the ion you have pushed in will come out. So you can modulate the color, you can change the color of this electrochromic window, which is most important for energy considerations. For example, today you have put a big screen over there. Instead of that, if you have an electrochromic window, just apply the voltage and you can change the color whatever way you feel like. The basic example what I have been giving you is that there is a charge transfer process which the Kelvin probe is able to measure. Now we have done one important experiment. How do you modify the surface? You have to modify the surface and you have to measure the surface. So what we did was, in fact our laboratory has been working very heavily on tin doped indium oxide ITO, which is very important. In fact, those who are using mobile phones, those who are using televisions, on that you have ITO in that. ITO is a transparent and conducting electrode, which is a multi-billion-dollar enterprise, and Samsung and LG, these people have pioneered in making those sheets of ITO. We also did some work on ITO. So what we did is we prepared ITO. These are the preparation parameters, and we exposed the surface of ITO with a plasma. This is a plasma cleaner, and the striking voltage is 550 volts. The applied power is about 30 watts. This is an oxygen plasma. Whenever an oxygen plasma goes into ITO, it changes its resistance. And we also have measured from the Hall measurements how much is the resistance change or resistivity changed on the surface, because this is a thin film. You can see the two plots. ITO before plasma, for example, if you see the z-axis, it starts with 0.1 volts, that is about 100 millivolts, and if you see this has shot up to 0.05, and there is an undulations on the entire surface. So what is going to happen is the surface not only got modified, we are able to map, we are able to characterize the surface of how the Fermi level is going to change. And we did also the Hall effect measurements, which showed clearly that the resistance of the sample is also changed. For example, this is the most important and I would like to say unique measurement ever has been done on the surface modification. So what we did was we plotted contact potential difference from a time t is equal to 0. What do you mean by time t is equal to 0? When the plasma is treated on the surface for about 10 minutes or so, it is plasma is treated for 35 minutes, and after 35 minutes we have switched off the plasma, took the sample, and we started measuring the Kelvin probe measurements. The moment we took the sample out from the chamber, plasma chamber, and put it to the Kelvin machine, it started showing 678, 680 millivolts as contact potential difference. Over a time t, means I just took it from the plasma chamber, kept it in the open along with the Kelvin machine, and started measuring the CPD. You see that CPD falls down as a function of time. We measured up to 120 minutes. The Kelvin machine, we made it automated, so it started recording it. Now, at the beginning of this, we measured from a Hall measurements what is the resistivity. It is of the order of 2.33 into 10 minus 3 ohms centimeter, and the carrier density is about 5.6 into 10 to the power of 20. These are all electrons, and Hall mobility is about 8.81 centimeters per volt second, and CPD is 0.683 volts or 683 millivolts. Within 2 hours, the contact potential difference has come down from 683 millivolts to 417 millivolts, and the carrier concentration has gone from 5.63 10 to the power of 20. It has come down to 6.7 into 10 to the power of 19. This, and also you can see the other parameters. The Hall mobility also has changed from 8.8 to 5.03. What is that we are trying to do with this experiment? If you have a sample, if you expose it to plasma, people say surface gets modified. It may be cleaned, but surface modification is there. How much modification has taken place, and what are the results quantitatively? Nobody has calculated so far. Because see the beauty of it. If you want to measure the work function, you have seen there are about 7 techniques. Say for example, angle resolved UPS. You have to take the sample, put it in the machine, start evacuating it, then you have to conduct the experiment with a UPS probe. It takes a lot of time. By that time, the surface has already modified. For example, you are taking about say 20 minutes to do the entire experiment. The CPD has already come to 580 millivolts. Means the surface starts relaxing, and once the surface starts relaxing, you can't really measure. So the question is, how much relaxation the surface is having? Can you follow the dynamic changes of the surface as far as electrical signature of the surface is concerned? Answer is this. Okay, there is no other measurement which can do this. Now you may ask me one more question. Why don't you go beyond 120 minutes? It is still showing a trend of coming down. How much more it will come down? It will go down. In fact, after about 48 hours we measured, then it got stabilized. So what is the point we have to take here? If there is a surface modification you would like to attempt, there is relaxation effects. So until and unless you make the surface completely relaxed, you may not be able to do any further processing to make a device. Otherwise device is going to fail. So a dynamic observation of what is happening in the surface is a very important result with the Kelvin probe technique. There is no other technique which will do that. So these numbers are very important. Before plasma oxidation or plasma treatment, actually we used oxide plasma, and after plasma treatment, you see the resistivity has 2.92 to 2.33, and after 2 hours 2.32. Now you may ask me, if you are really a good measurement person, these results may not mean anything, because there is an error in the resistivity measurement. So maybe within the error of measurement, it may not be the property of the surface. Okay, you take carrier concentration, there is a small change, and this change is not really that great. If you take Hall mobility also this way, that way, but the moment you come to contact potential difference, there is a drastic change, 0.097 volts to 683 millivolts and 417 millivolts. So what exactly is happening? The Fermi level is adjusting itself to come down, because the carrier concentration is coming down, Fermi level is coming down. That is the beauty of this experiment. So then we did one more thing. You said you can follow the dynamic changes. In fact, in the morning we asked a question: if copper is getting oxidized, it's not an instantaneous phenomena. Also, it's not a phenomena that takes quite longer time. can you follow the oxidation of copper dynamically? This is the question. I think all of you know, whenever there is a question, we have to do an experiment and get the answer. This is what we call research. So we said, okay, let us try. We took copper thin films, we made it by DC magnetron sputtering, and thin films do depend upon the surface energy do depend upon the thickness of the thin film. We all know about it. So what we did was we prepared two thicknesses. In fact, we prepared large number of thicknesses, and I am only presenting the data for two thicknesses for the specific reason I will tell you. We have prepared 200 nanometers and 1000 nanometers, and then these films are exposed to ambient in the air, and the thin film started picking up oxygen and get oxidized. Whenever they get oxidized, copper gets formation of CuO, Cu2O, CO3O4 because copper is multivalent. The one important stuff is whether the oxygen is adsorbed or absorbed, or ask a question whether this oxygen is making a bond with copper or just it is not making a bond, it is just sitting on the lattice and not making a bond. Even if it is making a bond, it is a very loose bond it is going to make. How do you know about it? These questions we said let us try to answer. The electrons from copper are exchanged with oxygen to form copper oxide. This is a charge exchange process. And remember, CuO is a p-type semiconductor. P-type semiconductor means the Fermi level is very near to the valency band. You get a large number of contact potential difference. This is the contact potential difference we got. CPD is positive for 200 nanometer copper thin films, and as a function of time t, we used to follow the oxidation process in this manner. After some time, it is going to get saturated. So almost it took about 60 minutes to 70 minutes to get oxidized, because it generally anybody can follow, because this is a first order kinetics. In the first order kinetics, initial oxidation is going to be much rapid, afterward it slows down. And the important point is this is a positive CPD. The moment when we go for 1000 nanometers, CPD became negative, and also the slope of the curve is going to change. You recall we have given two types of surfaces, anodic and cathodic. Anodic surfaces will have positive charge on the surface, cathodic surfaces will have negative charge on the surface. Naturally, these two positive and negative reactivities are being different, because thermodynamic equilibrium, the free energy of the surface and the Gibbs free energy for oxidation are different. So this experiment has answered the question. Following the dynamic oxidation of copper, not only the nature of the surface is known, but also the oxidation kinetics is known, and we are able to follow the oxidation kinetics, because these are not very fast, up to almost about 60 minutes beyond. Is there any other technique which can give you this type of experiments without really touching the surface? I would like to say probably there is no other technique. So this is one important point about Kelvin probe, and whether it is dynamic oxidation or dynamic corrosion, you know there are physisorption and chemisorption. Because I am not going into the details of these two techniques, I mean two phenomena. These two phenomena are clearly going to say how the oxygen is bonded to the copper lattice. Okay? Here I would like to say electropositive adsorbates, electronegative absorbates. So this is what I would like to call. For example, if you take, if the surface is going to be negative, the positive charge will be attracted, the chemical potential is going to go up, and if the surface is going to be positive, it is going to attract the negative charges. Again, the negative potential is going to go up, but negative potential is what's going to give you the CPD. So you can really characterize the type of surfaces whatever they are going to have. And adsorption induces changes in the work function, and absorption may not. So all these factors put together, whatever has been done till now about the surfaces, we can correlate it with the results of the Kelvin probe. Okay? We have categorized the surfaces, we have categorized how the oxygen is going to interact, and we did the experiment. The experiment clearly tells what type of reactions we are going to have in copper. we could be able to follow in copper because these reactions are pretty slow. If it is fast, you cannot. But there is no other technique where you can follow these reactions. That is the most important point. Now comes the important topic. This is the metal-protein interactions. This is a topic related to the biotechnology, microbiology, physics, chemistry, chemical engineering, and of course surface engineering. Precisely what you are asking the question is, if there is a metal implant in the body, it can be a dental implant, it can be a hip implant, it can be even a stent, how the proteins available in the body fluids, how they affect the surfaces of metals. These metals can be stainless steel, these metals can be titanium, aluminum, or whatever is the combination of it. Okay. You may ask me, don't you think that proteins are so complex, surfaces are so complex, so these interactions are multiplied by the complexities? How are we going to tackle the whole issue? It is because the proteins are completely different, but there are a few things that some proteins are more dominating. For example, if you want to say recent advances in electrode development for biomedical applications, the whole medical diagnosis is going to change a new area now. That is what is called biopotentials. Biopotentials will give you more important information about the physiology and about the what type of effects, what type of changes the cells are undergoing, because these changes are leading to complications later on. This is not a one-day process, this takes a little bit more time. So there is a lot of concentration on development of bioelectrodes or electrodes to measure biopotentials, that's a more precise, and to study the type of protein metal interactions, proteins not in general, specific proteins, so that there may be a possibility that we can see why some implants are being rejected by the body in some people and why it is not rejected in other people. So to say, what is that uniqueness defined by this rejection of the metal protein interactions in some body fluids, which is not understood yet at all. Now people are just making a compromise. If they are making a metal implant, they are trying to make a coating on the metal implant in such a way the body would like to say, okay, this is compatible with me. As I told you in one of the statements in the previous talk, we cheat the surface. Or for example, you take any metal, put gold on it. So the body fluid is going to see the gold and it thinks that is the entire implant, because interactions are confined only to the surface. How is it going to interact? Because even if you put gold, gold also is going to be oxidized after some time. That's what we have seen. So there is no guarantee that you have a gold. For example, most of you might have seen the dental implants. Some people use gold plated implants because gold is mostly very important, and also people when they smile, it's a golden smile, is it not? Of course, smile can always be golden, it increases the face value, but with gold it will be the golden face. That's all. The danger also is there. If you happen to travel alone in a train like me yesterday, if I have a gold implant, probably I would have come here, but I would not have been talking to you. Okay, so this protein surface interactions is an emerging area, and if you happen to see, Medical Council of India as well as the Department of Biotechnology is giving a lot of importance, and this is an area where you can really apply good projects. And what all the processes that take place. I am taking it from different journals so that you can understand the problem as a comprehensive view. If you take a metal implant, we can look into adhesion, signal transduction and necrosis, all sorts of medical terms which I don't know. And so there are lots and lots of things that are happening with the metal protein interactions. So if you have a microbiologist or a biotechnologist by your side, they may not be able to interpret the data because their knowledge on their understanding on Fermi levels is low. But if you combine with a biotechnologist or a microbiologist, both of you combine together, you will be able to get quantitative data of charge transfer between a specific protein and a specific metal surface, which is lacking now. I don't say lacking, but which is in the infant stage. Still a lot of studies have to be done. We can also say how the charge transfer process is going on with electron shuttling, conductive nanowires, direct contacts, because the beauty of it is now nanomaterials are being used, a lot of metal electrodes are being used to probe biopotentials. Also there are a few things, for example, if you take a few bacteria, a few pathogens, they form a biofilm. What is a biofilm? It is a protective film on the bacteria which will not allow any drugs to attack it. So it still resides on the surface and you may not be able to push it out. How the biofilms are formed on the metal surfaces and what are their effects, people do not have complete knowledge about it. So we thought probably Kelvin probe is one of the powerful techniques to use that metal protein interactions. What we took was, we took a material which is being used as a metal implant. We took a material which is being used as a cell culture material, and we started interacting with a known protein. Known protein is bovine serum albumin, which is a simple protein coming from the cow. That we treated the titanium as well as indium tin oxide and saw what are the changes. So to give you an idea about how the pathogens are forming or bacteria cells form biofilms, this slide is going to explain a little more. The main intention of showing these slides, with the note that I am not an expert on these biological materials or biological processes, but I would like to emphasize there is a new technique available which can actually give you how the process is going on, how the metal surface is getting changed. And that measurement is being done without touching the metal surface. That is the beauty of the technique. A simple example is, there is anodizing of titanium oxide. For example, titanium is a biomaterial, all of us know about it. Why only titanium? Because titanium is very light and it is very strong. If it is heavy, if I have a heavy implant on my leg, I can't walk usually, I have to drag my feet. Everybody knows that I have a metal implant in my body. Whereas if I use titanium, it's light. So titanium is being used. And titanium, whatever you do, there is a small titanium oxide film grown on titanium metal, whether you like it or not. So there were some studies, if you grow a intentional titanium oxide by anodization, how does the work function change? If the work function is going to change, it can also affect the growth of the biological materials. This graph at the bottom is going to show you, on the y-axis we have the work function of titanium, and on the x-axis we have made it increasing anodizing potential. For example, 30 volts, you get this type of honeycomb structures, 40, 50 volts, 60 volts. This is the anodizing voltage, and about 100 volts you get big honeycomb structures. So remember, go back to our previous question. If there is an oxygen on the metal, charge transfer process took place, Fermi level either goes up or comes down, so there is a change in the work function. That exactly what is being done here. We measured the work function and it is going to change like this when there is a change in the anodization voltage. What is anodization voltage of titanium oxide is going to produce? It produces different thicknesses of titanium oxide. The moment the thickness is changing, Fermi level also is changing. That is, so a charge transfer process took place. So this is going to explain our hypothesis, and the area occupied by the bacterial percentage also is seen here, and there seems to be a small correlation between the sample voltage or the increasing anodizing potential with the area occupied by the bacterial specimens and the work function. There is a correlation. So coming back to our experiment, we have taken ITO and TI, titanium. We have treated with bovine serum albumin, and we have seen how it is going to change the surface work function. This is, ITO is indium tin oxide grown by magnetron technique. We have taken about 15 samples, and you see when 0.1 milligram per milliliter of bovine serum albumin is there on ITO, the CPD is changing like this, is all negative, and before wash and after wash. So before wash, it is going to show about minus 175. Even after wash, that still remains on the surface. It means it is sticking over there. Similarly, 1 milligram per milliliter, 10 milligrams per milliliter. And if you do it on titanium, the results are going to be completely different. This is before wash, and after wash it has gone. Means with the titanium, it is not behaving exactly like ITO. This is a completely different surface. So these two are compared over here, and we have also measured here this surface energy. Nitinol is for stents. Yeah, what we did was we have not done the experiment. In fact, we have done the experiment mainly to show, the purpose of this experiment is to show that Kelvin probe can measure the changes of the surface, and we took two surfaces. One is titanium, which is a standard biomaterial. The second is an ITO, which is a standard biomaterial where you can grow the cells, because growing the cells you need a base. That base, people are taking it as ITO, and ITO is prone for making these cells grow. So we have only shown the basic power of the technique. In fact, if you ask me how nitinol is going to behave, we have to do the experiment. We have not done the experiment. In fact, this will open up a completely new area of how the surface behaves with the Kelvin probe, because this is only the beginning. And how the surface is behaving with protein depends on two factors: the nature of the protein and the surface energy of the metal surface, whatever we are dealing. So we have measured the metal surface energy also. There are so many other parameters, not only pH. You are absolutely right. When we control the entire thing, because we have tried to do it with pH of 6.7 in all our experiments, trying to keep it as neutral as possible. But for example, if the pH is going to change, for example, the pH of the blood is constant. It won't change. If it changes, we are not here. So most of the body fluids, the pH, except in the mouth, most of the body fluids, as I understand from the medical terms, it remains more or less constant, more or less. Yeah, because for the blood, if the pH is changing, we are not here. We will be somewhere else. It will not change at all. So what you said is right. So the basic aim of the experiment is whether Kelvin probe be able to measure the changes or not. For example, I shown you the first experiment with plasma treatments. The surface is going to change. We have measured it. With the plasma, with the oxidation of copper, we could find out the dynamic changes of copper. Now I am going to show you, if there is a protein on the metal, how is it going to change? It's only an example. It's not that if you want to go deep into the study, yes, this study opens up like anything. So yeah, maybe I would like to go back and come back a little. Yeah, fine. So to estimate the, see there are two things, how the surface is getting modified, how many number of BSA molecule adsorbed on TiO2 agglomerates. Because if you look at the problem, complexity of the surface, complexity of the protein. I put some protein on the surface. How the surface is going to react, how many protein molecules are or how many charges it is going to absorb. These two are most important points where I have to quantify. If I can quantify, yes. There are also methods to quantify. For example, BSA hydrodynamic diameter is about 6 nanometers. We have done Bradford's method to get the BSA added TiO2 aggregates. Oh, okay. Or should I close it and I was thinking, I was looking at this, so I was it started only now or even earlier?
This is the second batch.
Okay, okay. Got it. Thanks. There are software bugs. Huh? Okay. Okay. So we know the complexity of the surface, we know the complexity of the protein, and there are methods available. We are adding one more method to the available method, that is a Kelvin probe, which is more powerful. In the sense, it won't change the surface. So what we did was, there are many things mixed up here. For example, if you prepare a film, a thin film, at the same time on two different substrates, the thin film will have different properties. Why? It is very easy to ask a question why, and it is very difficult to answer this question after working for 6 months. Uday found out the answer. The surface energy of the substrate plays a major role in forming a thin film. So therefore, the properties are going to be different. So therefore, what we did was, if the properties are different, let us find out how the surface work function is going to change. So what we did was, we have taken a plastic substrate called Lexon, we have taken a glass substrate. On both the substrates, at the same time under identical parameters, in the same chamber, at the same time, we deposited tin doped indium oxide, ITO. What you expect, because it was done at the same time, both the thin films of ITO should behave whatever be the substrate. It's not according to physics, because substrate has got some surface energy that decides how the thin film is formed, which is a topic called nucleation, growth, and kinetics and thermodynamics. That is a most complex subject. Recently I was trying to compile all the information in one of my books, new books on cold plasma and nanometer. That gives us an idea. The problem is not so simple, it's very complex. And here I have seen, with just by changing the substrate, the complete CPD is going to change completely. And on that we have applied plasma, and plasma is going to behave in a completely different fashion. ITO on glass, protein on ITO. Then you may ask me, there are 7 methods of measuring the work function. Why don't you measure the work function in a different method and compare it with what you have in Kelvin probe? So we took all the samples. We have taken scanning Kelvin probe force microscopy. There, which is name may be difficult, but this is an attachment coming with atomic force microscopy, AFM. There is a small program available. If you plug in the program, you get the surface work function. So we did that. We did that on all the samples, whatever we have done. In fact, to give you the difference, now you may ask also, what is the difference between scanning probe Kelvin force microscopy and scanning Kelvin microscopy? scanning Kelvin microscopy or Kelvin microscopy is between two capacitor plates. Scanning Kelvin force microscopy is between the electrostatic force between a tip and the sample. I will show you that. Say for example, electrostatic force in a capacitor, you can say the force is dou C by dou Z into V square, or force is equal to the rate of change of the work done along the axis, dou W by dou Z. And the force is equal to Q multiplied V by D or C by D into V square. So we are dealing entirely a different basic concept in Kelvin force microscopy compared with Kelvin microscopy. So this is the most important. The electrostatic force gradient is important in Kelvin force microscopy. There is no electrostatic gradient. There is a charge transfer process and the potential which has been developed in Kelvin. These two are two different concepts altogether. So please keep it in mind that KPFM is not the same as Kelvin probe microscopy. So we got the pictures. I will show you the result. Yeah, these are the results. You see the first column is what the samples we have, ITO on glass, on a glass substrate. On the same sample we have put bovine serum albumin, and we have prepared ITO on Lexon under identical conditions, and we have treated the sample of ITO on Lexon with oxygen plasma for 35 minutes. Now you see the work function by Kelvin probe is changing in this fashion, but I cannot really correlate it because this is not a correlated experiment. What I ask you is compare this Kelvin probe work function data with the SKPFM data. This is 4.79 and this is 4.69. What is the difference? The scanning probe force microscopy gives you localized surface work functions, localized, whereas Kelvin probe gives you the average over a large area. Why I am stressing this point is generally when you send this manuscript to a publication, the reviewer says both are work functions, both are surface work functions, explain the difference and you try to correlate. It can't be done because two techniques are different, two areas are different, two methods are different. And from this change in work function from SKPFM, you may not be able to get the quantification data as you get in Kelvin probe. Make it a very important point. So yeah, I think the same picture. Yeah, this tells you how the protein is going to affect. For example, Kelvin probe work function is 4.796. Of course, we have seen 4.67, and we have measured the surface energy of this ITO on glass. That is on ITO we have measured. How do you measure? These are standard methods are available. I have these methods. Yeah, this method is what is known as von Osm theory. You take three liquids, and from these three liquids you take how much is the contact angle. By calculating from the contact angle you get the surface energy that we have calculated. When the surface energy is 37, the Kelvin probe work function is 4.79, and the other technique has given 4.67. When you put 0.1 milligrams of per milliliter of BSA on ITO, the work function has come down to 4.77. Remember, 4.77 can be easily measured from 4.79 because we are working on somewhere around 10 microvolt area, and it is almost of the order of about a few tens of millivolts. So it can be measurable, whereas the force microscopy could not measure the data at all, AFM data, and the surface energy is about 43.7 millijoules per meter square. Similarly, if you put 1 milligram per milliliter, it has come down to 4.75. If you put 10 milligrams per milliliter of BSA, the work function has come down to 4.7. Now see it very carefully. The moment you put the protein on the metal surface like ITO, the work function is going down. And it is after washing. In the sense, it is not that you just put it. Means to say, this protein has brought in some permanent changes on the surface. And from this change in work function, you can also calculate how many electrons have been transferred from the protein onto the metal, or from the metal onto the protein. Okay. These are some of the results. Same results. BSA, how it is going to do it on titanium, how it is going to do it on ITO. It is all here. The important point is there are changes. Those changes can be detected easily by Kelvin probe. That is the message we would like to take home. We have done only with one protein, BSA. No, we cannot, because if you make it with all proteins, what happens is each protein is going to behave in a different fashion. So first you have to understand each protein. I mean, probably the biotechnologist or a microbiologist may be able to tell you how many chains are there in the protein and how many electrons will be transferred. If that is known, we can calculate, because I am not knowledgeable so much on protein chemistry. The important point is, if there is one type of protein on one type of surface, you get lot of changes. This is only for standardization. In fact, to show that the technique works. If you have a complex protein, if you know the complete details of the protein, you cannot, because there are a lot of theories and lot of studies are available, how the protein is going to interact. For example, somebody has done on cyclic voltammetry, electrochemical techniques. But what happens is there, whatever is the change, that's all. And also you cannot simulate the exact experiment. Now what you are doing, you take a metal surface, put the protein, measure it, wash it, measure it. There it is not. You put the protein, make a voltage for that, so that there is an interaction between it. It's all electrochemical. We are not doing any electrochemical. We are just telling a virgin surface, virgin protein, how they interact. If it is complex protein, yes, there are methods available. But we have to ask the biotechnologist or a microbiologist. The important point is, can we do something with the biological materials? Yes, there are some scanning Kelvin probe microscopy for biomaterials and biological samples. So don't get the impression that only inorganic substances can be done. It can be done on biological materials as well. For example, biological materials are more complex and the technique is simple. Phenomena may be complex, but by making a good experiment, we can understand how exactly it goes. That is the beauty of Kelvin probe. Okay? In fact, whatever I am telling you about metal-protein interactions, it is the first time, or I would like to say a detailed description is being done for the first time on Kelvin probe in this forum, only here. Not that it is a secret. Over the time of last 4 years, during the pandemic and after that, we studied a lot, lot of literature, and this literature we have to do the substantiation. We have to do lots of experiments. Since I don't have access for lots of experiments, this is one of the reasons why I would like to come to NIT Warangal to seek your help, to seek your support, to seek your cooperation in conducting these experiments, so that the entire knowledge on metal protein interactions can be furthered and it can be done in a more elegant way. That is the main idea of my coming over here. Okay, good. You got an impression? Yes, Kelvin probe can be able to do wonders. But pardon me? Absolutely. Yeah. Can I ask your name? Janaki Raman's question, because Dr. Yadagiri, because there are some people on the YouTube also, they would like to know. So I'm just elaborating the question, I'll answer it. Dr. Yadagiri's question is, scanning electron microscope also does the same thing. Scanning electron microscope also does the same thing. Corollary. What is so great about the Kelvin probe? Or correlate the Kelvin probe with scanning electron microscope. Am I correct? Correct. How do you do the scanning electron microscope? You put the sample and then you have to evacuate. You have to evacuate, and the probes are electrons. Depending upon the charge currents of the electrons on the biological specimen, you are going to see the images. Okay? There you get the actual image of the metal caused by the biological sample or the cells. In Kelvin probe, you don't use vacuum. It is an ambient technique. Being ambient technique, the surface is not getting modified. Number one. Number two, you are not getting the direct image. What you are getting is the image of the Fermi level. What is the advantage of the image of the Fermi level? The electron transfer from the metal to the biological sample or biological sample to the metal, that phenomena is probed more deeper, because you know the quantitatively how many charges have gone in. For example, if the same biological material under vacuum may not be able to bring in these changes, or because of vacuum there may be other changes incorporated in the surface which I do not know. I am not knowledgeable about it, because vacuum can do some modification on the surface, electron beams can do some modification on the surface, whereas Kelvin probe, we are not doing any modification of the surface, we are just taking the measurement as it is. So the advantage of Kelvin over the scanning electron microscope is you get the Fermi level mapping, you get how much charge has been transferred, and you also come to know whether the surface of the metal is anodic or cathodic. Yeah, absolutely. That's a good question. When you put the biological material on the metal, under what conditions you are putting is your question. You can change the pH, you can change some of the concentrations like what we did. The same thing under these identical conditions, if you can conduct this experiment in scanning electron microscope, you get the picture of the surface in a more detailed fashion. In Kelvin probe, you get the phenomena, the details of the phenomena of the charge transfer taking place under these conditions. Say for example, you have put some biological sample at a pH of 6. Same thing you have put at a pH of 7. pH of 6 and pH of 7 are going to control the chemical reactivity. The chemical reactivity is nothing but the charge transfer process. With the 6 pH, the number of electrons transferred from the biological sample into the metal are different when the pH is 7. So if you study it as a function of pH, you can come to know what is the reactivity of this biological sample with the metal, which is not possible in the case of scanning electron microscope. Scanning electron microscope under these conditions will give you an image, but the image interpretation with reference to the electron transfers is difficult, whereas here it is very easy. These are the advantages and I can say disadvantages of both the techniques. Did I answer your question? Great. Morning we were started with bio implants or medical implants. So naturally you would like to ask a question, have you done anything on the implants? If so, show us. Here it is. This is a rejected implant from a human, from a body, from a patient. And what happened was it was implanted. After 2 days there was a lot of inflammation and the patient could not bear the pain and the whole leg had been swollen and the implant came out. It was actually screwed. There are about 8 screws. I am physically not showing you the picture, I have the picture. So why it has come out? The same implant bought from the same company, working nice with the other patient. Why not this? Was the question. Then we took this implant and we studied the CPD, that is contact potential difference, at different places. This implant is made of titanium, very costly implant, And we could see lots of differences, and we could see some places where it got oxidized, heavily oxidized. This is one implant. This is another implant. This also is a similar phenomenon. These have been done as a sort of research project, but this is actually what is happening. So to say, if an implant has been rejected, that shows a little bit of biocorrosion. We don't know the reason why at this stage, because we don't know the patient habits. In fact, some studies have been done not through Kelvin probe. It depends upon the body fluid constitution. Body fluid constitution depends upon your diet. For example, you eat lot of fish, you eat lots of other materials. Accordingly, the body fluids pH changes, reactivity changes. So, every human body is unique. If the human body is unique, how do you guarantee, how do you get the biocompatibility of the implants is the basic question. There is no answer for it right now. I don't know, at least there may be an answer, but I don't know. The contemplation is, can Kelvin probe be an answer for it? We have to think a lot. But if you make some studies of this nature, these are going to be extremely important, because today any rejected implant, any studies done on rejected implant mostly have been done with scanning electron microscopy. What they do is they take the implant, they cut the specimen, they prepare the specimen, put it onto the scanning electron microscopy, and there are lots of studies. But my point is, the moment you take the specimen, cut it and put it in scanning electron microscopy, the surface got modified. You may not get a realistic picture of what is there, but you may get a corresponding picture of it, not a realistic picture. Why not we do the same experiment with the Kelvin probe and get the realistic picture? I mean, that is the question. So this is an important point I would like to make to you all. If any of you are interested in this, this is going to be a great study, and people will really fund it. Fund it for the fundamental understanding. I don't mean that you take a rejected implant and do it, but you can take it on a metals which are used for implants. For example, as you rightly said, stents and hip implants, dental implants. Dental implants, whatever you said is absolutely right. The pH of the salvia is going to change a lot depending on what we eat. And it is going to interact with the implant, and the implant is going to be a metal, and this implant is not going to be on the top surface, it also goes deep down into the bone. So these are all some of the studies where we really feel a lot more can be done, which is of fundamental importance. Anybody, any funding agency will be very happy to fund these projects. Okay, this is my opinion. I got a project along these lines. And me? Biocorrosion means any metal interacting with the biological fluids, giving rise to oxidation of the metal because of the charge exchange process between the body fluid or the biofluid and the metal, is called a biocorrosion. And the biocorrosion is positive in many cases, is negative in some cases. If the biocorrosion is negative, the implant is rejected by the body. Then comes all the problems. Because if I have a hip implant and if it is rejected, as a patient I can't withstand the situation, because for about 48-72 hours I have to undergo the pain. It's terrible. So if we can predict the biocorrosion of this unique body before the metal goes in, then we may be able to make progressive or progress in making implants work for a given length of time. Today we can't say. Today we will put an implant, I mean medical doctors put an implant. If it is rejected, it can be rejected for several reasons. The surgeon may be bad, which is a rare case. Nobody would like to make a bad surgery. Everybody would like to give a good surgery, but somehow it fails. The body fluids are unique in such a way that there is a biocorrosion taking place. Then also it will. And sometimes what happens is the screws or the fasteners, whatever we fit in, they may give way. They may not be really tight. Most of the cases what happens is for the bone implants, when you tighten it with a screw, the bone may also get, the strength of the bone also matters a lot. I mean, these are all the points the orthopedics people will take care of it. But the important point is, today there is no real test whether a given implant is biocompatible to a given body or not. On the average, 98% it is biocompatible. 2% it is not biocompatible. If I fall under this 2%, I am unlucky. But with a life, why should you take this 2% as 2%? Why don't you take it as 100% and make it completely biocompatible is the question. Because nobody would like to say, okay, all operations are successful, about 70% are successful, remaining 30 are not. If you are falling in the remaining 30, I can't help it, come on, we will do it. It is a little difficult. At least for me, I cannot, I don't mind bearing the pain, but not going for a surgery like that. That is the point, okay? Your question is, is there any test to test the biocompatibility? Before inserting, to the extent I know, it is not, because this point is taken care by all the biomedical implants companies. They test it on several people. Of course, this is statistical, it's not unique. On the statistical means, they would like to say it is okay for 98%. Because 98% is a good percentage, but I don't want to fall in that 2%, and I mean, I have a fear of that 2%. That 2% fear is not really small, it's a big, so far it has not been developed. Probably when you are asking, can I take 5 more minutes? If you are asking that question of biocompatibility, I would like to draw a parallelism about 35 years back. 35 years back, if you want to get your spectacles, we don't have testing mechanism. Testing mechanism for the eye, testing mechanism for the lenses that have been made. So there are 2 machines are important. One, you have to test the eye, other you have to test the lens made for this eye. Again, every human body is unique. So today you go to any ophthalmologist shop, you say you want spectacles, he will ask you for a prescription, and it is called a prescription lens. The prescription lens first characterizes your eyes, then suggests what type of lenses are to be used. After getting the lenses, they will test it. This is what is called prescription lenses. To the extent I know, there are no prescription implants. What do you mean by prescription implants? You have to get exactly the same size as per the patient, and you have to get absolute biocompatibility as per the patient. So you need machines for that. For getting absolute size, today you have the machines called 3D printers. If you give a 3D printer exact dimensions, it will print and it will give you exactly what you want. But still you are lacking this biocompatibility test for that particular patient. So we are a little far away from prescription implants. That is where we should work. And this may not be able to be worked with medical people alone. Like physics can, because this is a complex problem. Problem is protein metal interaction. Protein metal interactions, all people have to contribute and then collaborate and then get a final solution. That's not coming. So probably with the interdisciplinary research being encouraged now, these type of studies are going to take more importance. And suppose if a group of people among you are coming forward to propose a problem, on these metal protein interactions, maybe with the help of a medical doctor. If you are all interested in it, probably I can also contribute my whatever a little I know along these lines, and we also have 1 or 2 orthopedic surgeons who are interested to work along these lines. It's a good idea to work. I mean, that is the summary I would like to give you. Okay? I didn't get your question. No, these are all the commercial implants. Whatever I am showing you are commercially available. They must have made all sorts of tests, then only they will get the approvals to come into the market. So all these things are absolutely tested. Only point is every patient is unique, and the point of biocompatibility is not guaranteed 100% on every patient, but it is guaranteed almost for 98% of the patients. Only 2 or 1% of the patients do not fall under this category because of the uniqueness of the patient, not because of the uniqueness of the implant. It is uniqueness of the patient. So in order to bring in the uniqueness of the patient, can there be a prescription implants is the basic question, because your spectacle lenses are prescription lenses. Whatever I use, you cannot use the same lenses to you, which we were using 30 years back. So the main question is, can there be prescription implants? How do we work along those lines? We need some machines. Probably this machine may work, but certainly it works on metal protein interactions. Metal protein interactions are fundamental to any of these biomedical implants. So that is the story. Okay? Why not? In fact, there are animals who have got a lot of implants. Yeah. In fact, veterinary doctors do have lot of implants also. They do. Naturally, because every human body, every animal body, every body is unique. Unique in the sense the body fluids chemistry is unique. Whatever the chemistry you have, I don't have the same chemistry. So it is there. We have pets, they meet with accidents, and people do these fracture implants and everything, even for the pets. No doubt about it. Because the number of pets and these type of clinics are rare. Have you ever heard that there are hotels for the pets? There are. For example, I was in Portland, and I could see hotel for pets, and I could see each pet has got its own room. And see, the point is the following: when you go outside, you can't take the pet with you. Where are you going to leave it? So there must be pets, there must be hotels, and I have seen one in Portland, and it is having about 200 rooms. And depending on what you want, you can put the pet in a room or whatever you feel like. And they give a specialized food for it, whatever you prescribe. It is better to be a pet. Huh? So this is what I think. I'm almost at 5 o'clock. Yeah, this is, I would like to make it as a summary, because I have part 4, how to interpret. Probably I have done it. Let me go through it very quickly. Yeah. Now if you can have a little bit of patience, can I go into the equation, so that if I don't show an equation, people may say that I don't know physics. So I should be cautious myself, and some equations I will show. Whatever equations I show, I would like to say finally, this is what are the most important stuff. Let me see that. Yeah, these 2 equations are going to be extremely important. That will show me how the EF EF is the Fermi level, is going to change. I can calculate N is the number of charges which are transferred, NC is the number of charges which are originally present, and P is the holes which are transferred, and V is the original holes in the material. With these two equations, I can quantify how much charge has been transferred from the metal to the object, whether it is organic, inorganic, biological, whatever it is, I can be able to calculate. Those who are interested, please let me know. I will be happy to give you more details, and I think, yeah, I'd like to stop it at this point. And one important point is, those who would like to know more about this Kelvin probe, both in terms of basics and instrumentation, the copy of the book which we wrote is available with Uday, and you can borrow it and you can read it. If you want a copy by yourself, please send an email to me, and I'll be very happy to send you at a small price. Okay? I said a small price because this book is published by two people. One is by Annie Books in India and CRC Press in US. My concept of a book writing and book publishing is the book should be affordable by a research scholar. What do you mean by affordability? If the research scholar can go for a dinner with his fiancée, how much he can spend, he should be able to spend it on the book and should be able to get the book. I did not say who pays the bill. Okay? So the price of the book is fixed at around 700 rupees in India and about $100 in US. Okay? But if any, most likely I'm going to provide a copy to your library tomorrow, and you can borrow it and you can use it. Okay? I have some more material, but I don't feel like going. It's already 5 o'clock, and 5 o'clock is my limit. Am I right? Okay. Okay. Already I spent almost about 2 hours after our coffee break. So I must really thank you for your patience and what should I say, giving me this opportunity to be in front of you to give my ideas. And it's a wonderful day, and I must have bored you, some of you, sorry about it. I must have excited you some. Keep the excitement, and I tell you, this is the most exciting field of doing new experiments, and some of you must have got a good sleep. Thank you, thank me for that, and I would like to say thank you very much. Thanks a lot. You may need this.
Hello. Thank you, sir. It's my great privilege to give vote of thanks to the chief guest, Professor A. Subramaniam, retired professor, Department of Physics, IIT Madras. He enlightened us with the inspiring talk on Kelvin Probe force microscopy technique, non-contact and non-destructive surface analytical tool with an introduction to protein-metal interactions. Sir made the lecture very interesting by dividing into 4 parts and explained each in details. Starting from the surface and interfaces, about the oxidation and corrosion, then explain the basic principles of Kelvin probe, talk about the work function of bulk as well as surfaces, which will be very useful for researchers, and given a brief lecture on different techniques for measuring the work function. Sir also explained about how protein and metal interacts with each other, how their surface potential modified when they come close into close contact with protein. And so overall through this lecture we are now able to understand the work function, how they changed, how they modified protein with like protein metal interaction and implants in our human bodies. So thank you, sir. Thank you giving this lecture. I also want to thank Dean RNC Professor Somasekhar for his presence and gracing the function in spite of his busy schedule. Thank you, sir. I also thank Professor and Head of the Physics Department, T. Venkatappa Rao sir, for his kind help in organizing this workshop. Thank you, sir. Finally, I thank the head TLC for providing necessary facilities to organizing this workshop smoothly. I also want to thank all the participants for participations through online as well as offline mode. Thank you all. Thank you for coming.
Thank you, Mr. Shiju. Now I request all of you to stand for the national anthem.